Okay, then statistical methods. Let's first review where we are. So we've talked about first level designs. And so far we discussed convolution for regressor creation. So how to essentially create one column of a design matrix. And then last time we also discussed looking at two regressors, so relationships of two regressors, so in terms of their orthogonality, correlatedness, or linear dependence. So if you want, first thing we looked at in terms of pictures is to get from stick functions to these predicted bold responses. That's one thing we looked at. And then if you put them into the design matrix and have one column looks maybe like this in the design matrix, and you have another column that looks like this, then we discussed some nomenclature about this relationship between the regressors, and we also discussed that linear dependence is kind of the crucial term in terms of the matrix calculus and matrix inversion that determines whether you can estimate your model. Now, the last thing in this kind of general approach to creating design matrices for any kind of experiment that you do is to look at one measure of statistical efficiency. Of a design. And that's the topic for the first hour today. I think 1 hour, that's definitely should not take longer than 1 hour. And once we're done with that, we will actually close this general discussion of design matrix, so first level creation, and look at a specific design called PPI, psychophysiological interaction analysis, that also relates to effective connectivity or whatever. So we looked at a more special case. So this is essentially then today the statistical efficiency, the last time that we talk about general first level designs that apply to all sorts of experiments. And things that you, whenever you set up your new fMRI study, should think about, and whenever you read a paper using the GLM for fMRI, should check whether the authors address these things or not. I hope you did the remaining examples and realized that in the future you will not just say the regressors are correlated, or if you say the regressors are correlated, that you actually mean that they are correlated, and you don't mean anything else, whatever. But you know that there are these terms. Now, the statistical efficiency criterion that we talk about today is a function of the design matrix. So the idea is that somehow you created some conditions, you created regressors, so you convolved your condition onsets, you have regressors, you chuck them together in a design matrix, and now you want to know, is what I've done, is that somehow good? Yeah. So you have a design matrix that, of course, this applies in general, even if you don't use convolution-based regressive formation, but of course in our case, it's usually intermingled. So you have a design matrix for your MR signal over n time points and for p conditions. And now the question is it good? And then, of course, so is the design good? Meaning also that the time when you present events corresponding to your specific conditions, is that good? And then the question for these questions, because these are typically questions that experimentalists start with, so they, of course, they put something together and then they are like, is that now good or not? And then, of course, some people are inclined to ask people that do methods, and then they ask them, is this good? And then the problem is always that the answer is it depends. And then my feeling is always that experimentalists go away like, the theoreticians have no idea. And that's but the question is, good in what sense? This is the problem. This is the whole optimality, goodness, whatever discussion. It's always the question, in which sense? And today I show you something that is, actually you find this in this chapter by Hansen. That's not the Bob group, but that's Rick Hansen. Bob. You don't know, you're too old, I guess, for Bob. Who knows the song Bob? You don't know the song Bob? Google this, Bob. Oh, Jesus, I'm old. Anyway, there was a band called Hansen with A that had a song that was called Bob. But there's also Rick Hansen, and he wrote a chapter in the SPM book that came out in 2007, and this discusses one measure of statistical efficiency of designs as encoded in design matrices, and this is what we look at today. And the important thing is that this is one specific measure of statistical efficiency and not the only possible or the right or whatever measure, but it's one. The idea behind this measure of statistical efficiency is to somehow address the question of better parameter estimate variability. So remember from our discussion of the GLM before Christmas that in the frequentist setting, the better parameter estimates can be shown to have a normal distribution that have the following parameters. So, do you remember what this beta refers to? So this actually is, so if you watch the GLM lectures and also remember what we did before Christmas.
The weights attached to the single regressors.
That's definitely the case, yes. Now we have a beta head and a beta. So what's the difference between the beta head and the beta?
The beta head is the estimated parameters.
And the beta?
It's the predefined or presupposed value of the parameters.
Yeah. So I wouldn't call it predefined, but presupposed or assumed, because it's not something that. So definition always implies that a human defines something, at least from my perspective. If you say, okay, it's the presupposed or if you say predefined, then it's defined by God, because these are the assumed true but unknown values. Yeah. So remember again that whenever you compute, for example, an average, in this setting where you assume that data realizations are realizations from normal variables and you compute the average of this, this is conceived as an estimate for the true but unknown population expectation parameter. And the sigma square, does anyone remember what this was about?
It's the variance of the normal distribution.
Of what?
So distributions of the parameters?
No. So it's definitely a variance parameter. It's actually called variance. It's also called inference, not inference. I hear a lot of Germans always saying inference. Interference and inference. Anyway, I don't speak very great English anyway, but inference always makes me a little bit crazy. So it refers to the variance parameter of a normal distribution, but the normal distribution of what in the setting of the GLM. Of course, here it's also somehow involved in a covariance parameter. That's true. So if you look at the variance parameter here, then of course it's the covariance parameter of the beta hat, but the sigma square does come from somewhere. So where does it come from? So it's not just invented for this distribution here, but it's referring to something else.
The variance of the errors.
Exactly. So that's the same parameter that governs the error normal distribution, which is centered on 0 and has a spherical covariance matrix with this variance parameter. Yeah. So this expression for the frequentist variance of the beta hat or the beta estimator is, first of all, it's has its expected value. It has the true but unknown beta values, meaning that if you sample many times from your assumed GLM and average all your beta estimates, your average will, in the limit of infinite sampling, approach the true but unknown values of the beta parameters, and the variability of the beta hat, so of the beta estimator, is dependent on the variability of the errors. So essentially this means if the data is very variable, then whenever you compute a beta estimate, or if you compute many beta estimates, then these many beta estimates also vary a lot because the data varies a lot. If the data doesn't vary a lot because the error contribution don't vary a lot, then also your beta estimates don't vary a lot. I'm always saying this is the frequentist distribution of beta hat. In a way, it's not completely necessary to say that, because in a Bayesian setting, so if this would be a posterior distribution, then there would not be a beta hat. So, but remember that this is not you shouldn't interpret this distribution that we look at here as a Bayesian posterior distribution. It's the distribution that you get if you would have the possibility to sample your GLM many times. In a real-life context, you only sample it once. Good. So this is the distribution. So for example, if your beta if you have two conditions, then you have a two-dimensional thing, and you can of course plot the distribution of your beta 1 and beta 2, so this normal distribution in 2D, and then depending on actually how this looks, this xtx minus 1, you will find either more correlation between the beta parameters or less correlation, like this, and then also depending on xtx and definitely the sigma square, you might have very little variability or you have high variability. Yeah? Of course, you can also look at that for only one regressor. That might actually be interesting. What do you get then? If you only have one regressor, then you have the dot product here, and then if they are orthogonal, you get 0. So orthogonality minimizes this, but if you are completely at 0, it's also not defined. Anyway, that's something I might look into at one point in more detail. Right now, I want to mainly stress the point that the distribution of the beta estimate, so beta hat, is dependent on the design matrix, and more specifically the covariance of this, so the multivariate variance of the beta estimate is a function of the design matrix and the error variance. Yeah. So that is the covariance of beta hat. Intuitively, you can see this as the variability of beta estimates. And now the criterion that Hansen proposed, and that is actually used, I think this is also used a little bit in the Thomas Liu work on optimizing design, is to say, okay, this variability of the estimates, this is something that we should try to minimize. Yeah, so we should try to come up with designs that by design, so come up with design matrices that by design have less or have little beta parameter estimate variability, because then if we measure once, then we still, it's just one outcome, and of course we don't describe the entire distribution that we could potentially get, but at least we know that extreme values that are far from the true but unknown value of beta are less likely than if we would use a design that induces high variability of the beta estimates. Now, the criterion is simplified further by not dealing with the entire matrix or some function of this matrix. So remember that XTX is how dimensional? What are the dimensions of XTX? So X is of course always n times P.
Squared or
no, XTX.
I don't know how is it this one or is it P squared? Should be n or P squared?
Yeah, but which one is it? Because it's the X is n times P.
So you have rows times columns or columns times rows?
Now you have the product of something that is n times P but transposed times something that let's make this is very wrong. So you have something that is n times P but transposed times something that is n times P.
That's P squared.
Yeah. So this is a P times P matrix. yeah, I know why I used to do always a lot of matrix calculus in the beginning, but then I always think maybe that's not that interesting. But anyway, so it's a p by p matrix. That means you have p squared, although it's actually a positive definite because it's symmetric. So you have p squared divided by 2 plus 1 or whatever entries, meaning you have more than one number. So to now define some measure of efficiency, you can either deal with the fact that you have a p by p matrix and somehow this encodes your efficiency, or you reduce that further by somehow summarizing this matrix. And the way that they do that, also for good reason, because it relates to the t-statistic, is to look at this matrix under the assumption that you want to look at a specific beta parameter contrast. This has two effects. So first of all, you tailor the criterion to specific contrast. So you might look at only beta 1, or you're interested in the difference between beta 1 and beta 2, or some other linear combination if you have more than, or for these, or if you have more than even more linear combinations. And so that's one benefit. So you make it contrast dependent, and you reduce it to a single number. And this then results in the following function, which is the letter xi, which is this criterion that is proposed by Hansen and people. So you take a contrast vector, you take a design matrix, and you evaluate a single number. So you put in a contrast vector, you put in a design matrix, and you project this onto CX, and you define this as the transpose of the contrast vector times xtx minus 1 c, and take this to the power of minus 1. So what happens here is essentially that, first of all, in terms of the covariance, so the variability of your beta head estimates, you don't take into account the error variance. So you assume, and that makes sense because you assume that you cannot really minimize the error contribution to your model, which is, it's a sensible assumption if you assume that the error contribution is the same over all different models that you can choose. Specifically, if you have just one design matrix in which you now play around with the onsets, it makes some sense. And if you assume, and this is the basic motivation, that sigma square is specified by nature, so that's error contributions that are always there. If you think about more, then it actually, this error contribution of course depends on your model, how well it actually defines or describes the actual underlying process. But intuitively it makes sense that you say, okay, sigma square, this is given by nature, that's a true but unknown parameter, I cannot do something about it. What I can deal with is the design matrix. So let's define a function that is a function of the design matrix, and then let's not look at the entire matrix, but look at specific entries of it. So one example for this would be that if you think about the covariance of beta, that this is, for example, coming out to be, how do we do that? for a 2D case, let's say, now let's do it like this. Yeah, whatever. So for 2D case, we have this. That's the covariance. And now we multiply with a contrast vector that we specify as 1, 0. Then with this contrast vector, what we get from the from the covariance matrix, not the design matrix, is of course if you plug this contrast in, is of course sigma square 1 1 times sigma square 1 2. If you do and this, and then do the other multiplication, so you isolate the first variance parameter here. So you isolate with, if you look at the contrast vector, weight vector of 1 0, you isolate the variance of the first parameter. So you don't look at the covariance between the first and the second parameter, you don't look at the variance of the second parameter, but you look at the variance of the first parameter. Yeah. So this is how this contrast weight vector basically takes out specific components of the covariance of the beta estimates. That's the criterion, and now you can, of course, come up with different design matrices that then result in different values of Xi, and then you can basically choose the design matrix that you like best. I will show you an example of that in a second. Before, I want to give another interpretation of this that maybe has even more applied value. Why this is kind of a good criterion, and this relates to the t-statistic. So the t-statistic for some contrast weight vector is of course given by the contrast weight vector multiplied by the beta estimates multiplied by the contrast weight vector divided by the variability of this contrast, which has exactly the same form as our criterion, only that there's a square root. And so essentially, if you minimize the variability of the beta head estimates, you get larger t values. Yeah? That's kind of a more experimentally oriented and academia-oriented thinking about this than a scientific thinking. So if you want high t values and something significant, and you want a great paper in Nature Communications, then you might play with the design matrix that in theory, it gives you higher t values than if you use another design matrix. If you are less inclined to be susceptible to academic arguments, you can also say from a scientific perspective, it makes sense that we minimize the variability of our estimate, because then we can put more trust into our estimates. If you're more like, we need a significant result, then this might also convince you that this is a good idea. Okay, now I want to show you an example of this. Questions? You're clear why we're doing this, right? So why are we doing this?
The T value is the alpha?
No, this whole statistical efficiency business.
What exactly you're addressing? I'm sorry, I don't know what exactly reason you're addressing.
So why are we thinking about this?
It's important to understand the analysis.
Yeah, in a way, and because of course it's important from if you do your experimental design that you think about in which order and not in which order, but at least when do I want to present my events. Yeah? So you need to, when you do an experiment, you always think when and how do I present my events, when do people perform the task. And of course this tries to explain in a way one approach to do that. Yeah. So this is important because I have the feeling you are a little bit like, no? You're happy or confused? Who's happy? Good, 2 people are happy. That's as much as I can achieve on a Monday morning. So this shows an example, and of course this is all implemented in the code. So this is actually fairly important. So I would really recommend, if you do a fMRI study in your master thesis, that when you set out to do your fMRI study and your supervisor tells you now program the experiment, and you have all these questions like how much time should I put in between trials, then this is actually the stuff that you should go back to and look at how you maximize your statistical efficiency, or what one way is to maximize your statistical efficiency, so that you do some rational experimental design. Yeah? So it's not completely just theoretical whatever. It's actually fairly important from a practical perspective. Now, to look at this, one can, of course, the thing is within experimental design, you have, of course, many free parameters. Yeah? You can look at the sequence of stimuli that you present, you can think about the cognitive processes that you evoke, or you have constraints like that you cannot do the experiment forever. In this case, what I'm looking at is that you look at the inter-event interval. So how much time do you allow between 2 events, like for example showing a face and then showing a house, then the question of what do I want to look at? Do I want to find brain regions that are differentially activated? So do I want to find the face area versus the house area? Or do I want to find brain regions that are active for visual stimuli? So essentially face and house areas together. This is then example. So what I did here is this with these 2 conditions designs that we discussed fairly early on, where we looked at brain mapping in general, where we have 1 condition and 2 condition. I created many essentially random orders of always the same number of stimuli. I think it's 1, 2, 3, 4, 5, 6, but there are many. Why are there only 6? Don't know. Maybe it's. I think it's only part of it. I thought it would always be the same number. Well, here it's more reddish. Not quite sure. Anyway, I generated random designs. With maybe it's with a different number of stimuli, but I do it many times. So on average, they have the same number of stimuli per each condition. There is a sampling function behind this that I now don't discuss. The thing is, essentially, I just generate many designs randomly with varying inter-event intervals. So either there's a lot of time between intervals or there's little time between intervals. If one does it with little time between intervals, you see the case here. So there are 20 seconds and there are a number of stimuli in between. If one convolves these onsets with the hemodynamic response function, you get these predictions. So the straight lines are the regressors, so your columns in your design matrix. If I allow for more time, then of course you don't get these overlaps of hemodynamic response functions or hemodynamic response predictions, so you have isolated events. So this is one example for long inter-event intervals. Now, then I do 2 things. Just for the fun of it, looking at the regressor angle and correlation. in terms of degree and correlation, just to basically look at the same thing as we did last time, to basically emphasize the fact that correlation and angle/orthogonality are not necessarily the same thing. What you see here is the correlation that is basically non-zero all the time. It's specifically between these two regressors. It's particularly strong if you have inter-event interval of 5 seconds, and then as you put the things further and further apart, the correlation reduces more and more. This is averaged over many instantiations of the designs with an inter-event interval of 4 seconds, 5 seconds, 6 seconds, and so on. So essentially what this graph says, if you take the events quite far apart in time, you have less correlation than if you have them quite close in time, which is not too surprising. But that's what this says. The more important thing for what we discussed today is in this graph, where I now look at this function C that we discussed here as a function of the inter-event interval, and for two contrasts. Yeah? One contrast looking at the sum of beta 1 and beta 2, so essentially trying to find voxels that respond to both faces and houses, and one for the contrast 1 minus 1, so finding voxels or brane areas that respond more to faces than to houses. And the efficiency is, because it's efficiency, it's supposed to be a large value, so large values are better, so high statistical efficiency is good. What you can see here is that the statistical efficiency depends on the contrast you are looking at and interacts with the inter-event interval, meaning for very short inter-event intervals, the efficiency for detecting something at all, so for the contrast weight vector being 1, 1, is quite high. So you're doing well if you want to detect just something. That also means that if you, for example, use block designs, so where you put stimuli quite quickly one after the other, you're doing well. If you are interested in actually finding differences in this event-related design, so this is now not talking about that you do blocks and then you do some rest and then you do another block of the other condition, but you intermingle them like in a typical event-related design, then you should rather use a little bit more, wait a little bit in terms of your inter-event interval, and be more something around, or you get higher statistical efficiency, definitely not in the very beginning, but it rises to a certain level, so which it actually reaches around 6 seconds or so, and then it stays at that. And you get actually higher statistical efficiency for detecting differences than detecting only the response to either stimulus, and at kind of this intermediate, or let's say 10 seconds of inter-event intervals. So this is an example where the statistical efficiency depends both on the contrast that you're looking at and how far apart you put them. This is only one way to do this and to look at this. Of course, you can come up with different criteria, more conditions. Maybe you are not interested in the inter-event interval, but in the order of stimuli, let's say. So this is supposed to give you a taste for what or how to optimize designs, if you want to optimize designs. In general, what happens usually is that you say, okay, let's somehow, so what a general, and this is also generally correct whether you do simulations or theory or not, in general it makes sense to randomize as much as possible, and it also makes sense to not have things too close together in time. So something about 6 seconds between events is definitely a good idea. That's kind of a rule of thumb, but you can, of course, if you have a given design, go much more into detail, either in optimizing or in the things in terms of optimizing. In the end, you have to be pragmatic, so you can, of course, think about your optimal design for the next 10 years and not do it. So I also wouldn't recommend this, but at least once you have created your design and now acquired data in a specific way, you can look at also in terms of if reviewers then ask you why was this done, why was that done, then you can say this was for pragmatic reasons, but we can quantify that we have this and this kind of statistical efficiency, for example. Then you have an answer. Good. This is, in a way, what I wanted to say about statistical efficiency. There are good papers. So there's work by Thomas Liu on optimizing event-related designs. There's some stuff by Tor Wager and Thomas Nichols on optimizing design. In the end, you will find that there are also toolboxes, so you can also use a toolbox to optimize the design. Did you use a toolbox for design optimization? I seem to remember something like this. No. But in the end, in the end, all of these things can be understood, and it should be what I'm trying to get clear is that if you are faced with the question, what is a good design? You need to specify what you mean by good. Then you can work out what is better than something else. If you can't say what you mean by good, then there also will not be an answer, because that can depend on many things. Okay? Statistical efficiency in terms of design. Questions? No? Then let's have a break, and after the break, start with PPI.